So does anybody want to volunteer to try to show? You want to watch me do one? Or you can watch me do one. All right, which one do you want me to do? The first one? All right. So you want me to show if this has delocalized electrons. So one way to look at this is to think about if you just have like a straight alkane chain, you're not going to have delocalized electrons, right? Because if you move electrons around, you're going to be breaking bonds. So the first thing you want to look at are electrons we could move without actually completely disconnecting two atoms. So we want to look at double bonds like these. Then we want to think, is there anything we could push those double bonds onto? Or not the double bonds, but the electrons in the double bonds. So like here on this oxygen, it's, you know, very electronegative, so you can push electrons onto it and it's still happy. So if we take these electrons and push it onto the oxygen that already has two unshared pairs, we would form this with a minus charge, but also that carbon, which had 3 bonds, now only has, or it has 4 bonds, now it only has 3. So there would be a positive charge there. And since we've got another pair of electrons here, we could also push that positive charge over onto that, right? So we could push that over to there. We could get this, and now the positive charge is on this carbon, because that carbon has 2 hydrogens on it, presumably. It's got 2 bonds to this carbon, now it's only got 1 bond to that carbon and the 2 hydrogens, so now it's got the positive charge. So you just want to look for things like this oxygen here where you can push electrons onto it. And these conjugated, as they're called, if they're 1 carbon removed, so you've got carbon in a double bond, 1 carbon over another carbon in a double bond, so double bond, double bond, like that, that's a conjugated system. If you've got a conjugated system and somewhere to push those electrons onto, you're definitely going to have resonance. You're going to have delocalized electrons. So this one is yes. I think it just asks, does it have it? Which of the following have delocalized electrons? So A has them. Does anybody want to come up and... There we go. And the 2 other new people who came in, did you sign in on the manifest? You ever been here before?
What?
Have you ever been here before?
In
the center?
Yeah.
Alright, I was just making sure you know that.
So, do you want me to draw contributors, or what do you want me to do?
You can do whatever you want, but overall you can do B through H, whichever one you want to do, and just say whether you think they have conjugated.
Okay. You mean delocalized?
So you could either say, like, put an X and say no, this doesn't, or you can put a check and say yes, it does.
Okay. So that one does.
That one does. Anybody else want to try? And at the end, I'll explain why that is correct. Anybody else want to come up? Come on, don't be shy. Get up here. Anybody?
Okay.
No, nobody wants to do it? Yes, you can do another if you want.
Okay. And that one does. And I feel like that one does, but I'm not completely sure about that. That's it. Alright. Totally believe that, but I think that's it.
Alright, so yeah, she got all the ones that did. That one does, that one does, that one does. And this one doesn't. This one doesn't. And neither of these two do. So, someone want to tell me why that one doesn't?
Well, you got a double bond, but they both lead to sp3 carbons.
Right.
So you just break that bond.
Yeah, you would end up just pushing off a hydrogen if you tried to move that either direction, because it could either move between these two carbons or these two carbons. But if you did that, these carbons are already saturated, so that would knock off a hydrogen. So that double bond is going to stay where it's at, right? What about this one?
More or less very same reason. Like there's a positive charge, but there's a carbon between the double bond and the positive charge. So if it tried to go over there, it would break it before it got to it.
Right, exactly. So they put that positive charge to try to mess with you, but it's actually 2 carbons away, so that double bond can only move over between these 2 carbons. So it has 1 carbon to go before it could give some electrons that positive charge. It's the same thing that's going on in this one, which is kind of weird that they give 2 examples showing the same thing, but I might have copied down one of the calculate structures into a bond line structure wrong, I don't know. But either way, it works. This one, also for the same reason as in B, these 2 double bonds are, 1, 2, they've got 2 carbons between them, so there's no way that they could throw electrons back and forth. Essentially, if you just have a straight carbon chain, even if you've got double bonds in it, you can't really have resonance unless where that double bond moves, the electrons can be accepted, which is what brings us to E. Where is the resonance in E? Where are the electrons going, essentially? The delocalized electrons.
Well, you've got a benzene ring, so
right.
That's where most of the delocalization is happening, but it also shares a bond with that other ring, so over there it can still share. So
right. Well, actually, this ring is saturated, right?
Yeah.
Each of these carbons have 2 hydrogens over here.
Right.
So if you tried to push one of those...
Oh, right, so it can't go over
yeah, the delocalized electrons can't go over into this cyclohexane ring, but in this benzene ring, they can go around.
Oh, okay, so they just can't jump over to the other side.
Yeah, so essentially in a benzene ring, you have each of these carbons has 1 hydrogen, and these are bonded to another carbon over in that other ring.
That's right, I forgot.
So each of them have 1 extra bond outside the actual benzene ring system. So if you move the electrons around in a circle like this, so we could redraw it like that.
So all the bonds would go.
Yeah, all the bonds would be over 1 position. Then each of these are still making 3 bonds in the benzene ring system. So we didn't have to. Yeah, we didn't have to break any bonds. So essentially, you can always work through these. Like, if you can move a double bond somewhere or a pair of electrons somewhere without breaking, like, you can break a double bond. Like in this case, we had a double bond here, and technically we broke that double bond by pushing these electrons up to the oxygen, but we didn't actually separate the oxygen from the carbon.
Because oxygen is so electronegative.
Right. So it could accept those. And also, it's just got unshared electron pairs up here. It's not bonded to a hydrogen or anything.
Oh, okay. And so
So-
the unshared electrons mean that you
Yeah.
can just...
Exactly. So, what else? What didn't I talk about? That one? Does everyone see the delocalized electrons in F?
Yeah, that kind of threw me for a second because it only has the 1 double bond, but it's got that positive charge right over on the other side of the double bond, so it can go over there if it wants to too.
Right. So does anybody want to come draw that resonance hybrid for F? Anybody? I'll start making people. The one other guy. Get up here. Yeah, so for F, draw the resonance hybrid. There you go. So is that the only resonance hybrid for F? I'll draw a little... Ooh. So it's going between those 2. Is that the only resonance hybrid F has then?
I think so, because the others are single bonds, right? So they would be able to accept that.
There you go. So we have this double bond moving here, and then we have it moving back that way. So it's just going between those 2.
Oh, okay.
How's it going?
It's going pretty good.
Yeah.
Good.